My name is Dr. Mike Murphy. I'm an assistant professor of computer science and information systems at Coastal Carolina University. In this lecture, I will continue the discussion of processes by introducing the fork, exec, and wait system calls. I will provide examples of using these system calls in both C and Python. Processes are created on Unix-like systems, such as Linux, by using the fork system call. This call is available as a C function by including the unistd.h header file. In Python, access to fork is provided by importing the OS module. In this C example, I fork a child process that simply prints a message. My code begins by importing the stdio.h and unistd.h header files for the printf and fork functions respectively. Inside my main function, I declare a variable named PID of integer type. I then print a message stating that I have not yet forked the parent process. I call the fork function without arguments, and I assign its return value to the PID variable. Upon completion of the fork function, I will have two copies of my program running at the same time. In the first copy, where I called fork, the value of the PID variable will be set to the process ID of the child process. In my child process, the value of the PID variable will be set to 0. My child process prints a message stating that it is the child. My parent process prints a message stating that it is the parent. Both messages will be printed since the value of the PID variable will be 0 only in the child process. However, the order in which the two messages are printed is not guaranteed and may vary between program runs. The equivalent Python code is a bit shorter but looks rather similar, owing to the fact that Python is exposing the underlying C library to us. To use the fork function, I need to import the OS module. I then set the PID variable by calling os.fork in a manner similar to the corresponding C code. Upon receiving this call, the entire Python interpreter process will be cloned. The PID variable inside my script in the parent interpreter process will contain the process ID of the child Python interpreter process. In the child interpreter, the PID variable in my Python script will have the value 0. Since the value of PID is 0 in the child process, the child message will be printed. In the parent process, where the value of PID is not 0, the parent message will be printed. Both messages will appear in the output of the script, but the order of the messages is not guaranteed and may change. While we sometimes fork processes in order to create parallel programs, a more common use of forking is to start another program. We can replace a currently running process with another program by using the exec system call, which is made available through a variety of functions in C and Python. One important thing to remember about the exec system call is that it completely replaces the currently running program with the new program. A common error is to try to put program code after a call to exec in an attempt to perform some other operation after the external program is finished. However, any such code placed after the call to exec will never execute, since that code gets replaced with the rest of the original program. Now, in practice, the exec system call is implemented as a collection of functions, not as a single function. These functions differ in whether or not they take arguments as a fixed set of parameters or as an array. They also vary by allowing the operating system to search the system path to find the new program, versus requiring the absolute path to the new program to be provided. Furthermore, some of the exec functions allow environment variables to be set for the new program. Regardless of the version of exec that is chosen, a standard convention on Unix-like systems is that the first argument to a newly loaded program is the name of the program itself, exactly as the user entered it. This convention allows a single program to be known in the system by a variety of names, possibly allowing it to implement different behaviors depending upon the name by which it was invoked. As I mentioned, there are quite a few variations in exec functions. In the C programming language, versions with a lowercase l in the name take a fixed number of arguments, where the final argument is always a null pointer of character type. Alternatively, versions with a lowercase v in the name take a vector or array of arguments. If a lowercase p appears in the name, the operating system will search the system path to find the new program. Versions with a lowercase e allow environment variables to be modified. The corresponding Python versions of exec, available in the OS module, follow the same conventions with respect to the lettering. However, it is not necessary to pass a null pointer at the end of the L versions. Now, let's take a look at a simple C application that forks a child that execs the /bin/echo program installed on the system. Nothing has changed about the fork operation. The PID value returned to the child is always 0, while the value returned to the parent is always non-zero. However, in the child, we are now using execl to load the /bin/echo program. Notice that /bin/echo is both the name of the program and the first argument to the program. The message to be printed, hello, follows. Finally, we must terminate the parameter list with a null pointer, which needs to be cast to a character pointer type. When the child calls execl, its copy of the program code is completely replaced by the code for /bin/echo. Thus, the child never prints the final message in the program. The message is thus printed only once by the parent. The Python version of this code is shorter but otherwise similar. There is no need, nor is there any practical way, to pass a null pointer to os.execl at the end of the parameter list. As is the case with the C version of the code, only the parent prints the message at the bottom. The copy of the Python interpreter and script that was created by fork is completely replaced by the call to os.execl with the code for the /bin/echo program. Thus, the child is no longer executing the Python interpreter, and the final line of code is never run in the child. We have seen that we can execute another program using exec. However, what if we would like to take some other action after the other program executes? In that case, we can use a version of the wait system call in the parent to wait for the child to terminate. Before moving to example code for wait, take a moment to note that, in some cases, the parent process may terminate before the child process. On a Linux system, termination of the parent before the child creates an orphan child process. Some programs are intentionally designed to create orphan processes. These programs are engineered to run in the background, performing various system services, and these are known as daemons or service processes. By convention, the word daemon uses its archaic spelling here with an AE in place of the E in the modern spelling. However, the pronunciation is the same. Daemon is incorrect, even though many people mispronounce it. Now, the C code illustrating the act of waiting on a child process to terminate barely fits on one slide. In order to get access to the waitpid function on Linux, I need to include the sys/wait.h header file. In this example, I fork a child process that sleeps for 5 seconds before exiting. In my parent code, I announce that the parent is waiting, then I call waitpid to wait for the child to terminate. In this simple example, I need to pass 3 arguments to waitpid: the process ID of the child, which fork returned to the parent above, followed by a null pointer, followed by the number 0. The waitpid function blocks, or stops and waits, until the child process terminates. Once termination occurs, the parent prints another message. The Python version of this example is considerably shorter, but Once again, it uses essentially the same calls. In addition to the OS module, I need to import the time module to get access to the sleep function. The major difference in this code from the corresponding C code is that I do not pass a null pointer as the second argument to os.waitbid. Instead, I skip that argument and simply pass a 0 instead.